Hello, I am Dr. Abhishek Sharma. Today I will discuss noise in frequency modulation. Consider a frequency modulated signal which is given by phi of fmt is equal to AC cos of omega ct plus kf integral minus infinity to t m tau d tau, where, where kf is the frequency sensitivity constant for the given modulator and mt is the message signal. Now the instantaneous angle for the above expression of frequency modulated wave, instantaneous angle is given by theta it is equal to omega ct plus kf integral minus infinity to t m tau d tau. Now the instantaneous frequency which is the derivation of the above expression theta it with respect to time is given by omega it is equal to d by dt of theta it is equal to omega c plus kf into mt. Now consider the block diagram of the frequency modulation. First we consider the transmitter of FM, and let us suppose that the antenna has transmitted the FM signal which is passing through a channel which is having additive white Gaussian noise. This is your channel. Phi of FMT is your incoming signal into this channel, and the noise is AWGN. This signal is received by the receiver antenna followed by a band pass filter. After the band pass filter, it is going inside to the limiter, which limits any amplitude variation of the received signal. And after the limiter, the signal is going inside to the FM detector, which is comprised of two circuitry, you can say, that is first differentiator and an envelope detector. And after envelope detector, which is FM detector, it is passing through an LPF, which is generally used to extract the message information, which is your baseband signal, and we get the actual signal S0 with S0 power, and N0 is the noise power. Basically, from FM detector to LPF, it is our main system. We have to calculate the noise analysis, or you can say we have to find out the noise analysis for this given section. Let us suppose that the input of the FM detector, the signal is SI and the noise power is NI, where SI is the signal power, and this is the node A, and that after LPF this node is B. Now we consider 2 points. The first point is the FM detector comprise a frequency discriminator I have considered this discriminator as an high pass filter, or you can say the derivative of the incoming signal is performed by this high pass filter, and which is followed by an envelope detector, which is usually we can say it is a simple diode. The second important point is limiter is used to limit amplitude variations now. For the noise analysis of FM, we can calculate the signal power and noise power separately. Actually, this process is somewhat similar to the superposition theorem, which you have already studied in network theory. I will mention this here, like superposition theorem of network theory. Now, first we have to consider signal power at the input, which is node A. This is the simple term, which is SI is equal to AC square by 2. It is so because S of t, for example, any cosine signal having amplitude A, the power of the signal is given by expectation of square value, that is S square t, which is given by A square by 2. Now, the signal power at the output will be calculated as, now as we know that the output is received which is proportional to the instantaneous frequency. It is clear that output of the FM demodulator is proportional to the instantaneous frequency because our messages lie in the frequency term. So the detector output is proportional to instantaneous frequency. Now as S naught T is proportional to omega I, which means that if we take the proportionality constant K, it will be equal to K of omega I, where K is our proportionality constant. Now the omega I will be equal to omega C plus kf into mt, which is again tends to that S naught T will be equal to k of, which is come from the above equation, k of omega C plus kf into mt. Now S naught T will be again re-equated as k of omega C plus k into kf into mt. Note that k omega C in this expression is a constant term. We have already considered that the incoming signal is first phase, the first stage of differentiator, that is your high pass filter, and the arrangement of high pass filter is such that it cannot pass any DC component value towards the output. So we can say that the term k of omega c is a constant DC term which we can ignore. Let us describe this in a block. You can easily understand this. High pass, stop, low frequency component, which is generally DC terms. Ideally, the gain is 0 for low frequency. Suppose it is, suppose that for DC component value, frequency value, the high pass filter shows 0 gain. Whole square. Now again we can re-equate the above expression E of k square, kf square, m square t. As k square and kf square is a constant term, we can take out from this expression E of something that will be equal to k square into kf square E of m square t. That is the average. So m square t bar is the root mean square value. This is not really root mean. This is the m square t's mean square value. Now, as we have already calculated two signal power, that is at node A, which is Si, and at node B, which is S naught. Si will be equal to AC square by 2, and S naught will be equal to k square into kf square into m square t bar, which represents the mean square value, that is the power of mt. Now we have to calculate the noise power at the input as well as the output terminal. The noise power the input noise power is evaluated for the base bandwidth Here base bandwidth is the bandwidth of the message signal, which I have already discussed that it is equal to B radian per second. So this is the bandwidth of the message signal. Is B. Now we have already discussed the different noise powers in the previous videos in noise part 1 and noise part 2. We have shown that in phase component of the noise have equal power with the quadrature component of the noise, which is equal to eta b by pi, and the band pass noise power will be equal to eta into b by pi. Now this is very simple, that the noise power will be given by Ni at node A. It will be equal to 2 into Fm into eta, where I have replaced the value of B is equal to 2 pi Fm in the expression of Sni. So this is the band pass noise power at node A. So the input noise power Ni is equal to 2 into Fm into eta. Similarly, we have to calculate the noise power at the output. To calculate this power, we will assume that empty is not present at the input, or we can say empty is absent at the input terminal. You can say in FM signal empty is not present. Now let input signal at node A will be given by GIT I'm talking about the node A, So G of IT will be equal to AC cos of omega ct plus NIT, where I assume there band pass noise is our NIT after passing through the band pass filter. Now as NIT is a band pass noise, we can replace it again with its low pass equivalent, which is given by NIT is equal to NCT cos omega ct plus NQT into sin omega ct. Now we will replace this value in the above expression. The new expression will be mentioned as GIT is equal to, we can take the common term AC plus NCT of cos of omega ct plus NQT into sin of omega ct. Now I am draw the diagram, which is first differentiator, and after that an a diode, which is an invalid detector, is connected, and then LPF. This is invalid detector. Now GIT will be equal to under root of AC plus NCT whole square plus NQ square T into cos of omega ct minus phi t. Actually, this expression is the trigonometric equivalent of the above expression of GIT. With the help of trigonometric identity, we have converted the above expression into in the form of envelope voltage and phase. So the ET is our envelope voltage, which is given by this expression, and phi t will be equal to tan inverse NQT whole divided by under root AC plus NCT whole square. Now the theta t of the above expression mentioned in GIT will be omega ct minus phi t. So the theta t is equal to omega ct minus phi t. And if you want to calculate the instantaneous frequency, we have to take the derivative of this theta t, which will be given by d by dt theta t is equal to omega c minus d by dt phi t. Now we have two cases. Case 1, where we can consider that AC is dominating over noise. That means AC is much greater than NCT and NQT. We can consider it a small noise case. And there will be again case 2, where noise is dominating over message. That means AC is much less than NCT and NQT. This case is considered a large noise case. Now, as the output of the FM detector is proportional to the instantaneous frequency, we can write it here. Now, the output of the FM detector it, it is proportional to instantaneous frequency. Now we have to consider all two cases, which is as defined above. For case number 1, phi of t, not psi of t, phi of t will be equal to tan inverse nqt divided by AC, which is a small noise case. Now as AC is much greater than nqt, the value of nqt upon AC will be much less than 1. So phi of t can be expressed as tan, which is tan inverse nqt by ACT. It will be re-evaluated as equal to nqt upon AC. Now the new value of phi of t for a small noise case is nqt upon AC. Now, as the output is proportional to the instantaneous frequency, that means your omega ct minus d by dt phi t. So we can replace this value in the above expression with the n naught t will be equal to n naught t is proportional to omega I, which leads to n naught t is equal to k of omega I, where k is the proportionality constant. Now we can replace the value of omega I from the above expression, which is n naught t is equal to k of omega c minus d by dt of phi t. That will be again equated as k omega c minus d by dt n qt divided by AC. So n naught t is equal to k of omega c minus AC is remaining. Okay, then come to the expression. It is minus 1 upon AC d by dt nqt. Again, n naught t will be equal to this was our omega I. Now we have to calculate the power spectral density of n naught t, which is directly depend upon the power spectral density of nqt. Nqt, let us suppose, have the magnitude spectrum or spectrum nq omega. Now its power spectral density, let us suppose sq omega, is directly proportional to the magnitude of nq omega whole square. Magnitude of nq omega square. Now to calculate the PSD, nq dot t will be equal to, or we can calculate it as, by applying the derivative property of the Fourier transform, nq dot t will be equal to d by dt nqt. So we take the Fourier transform on both sides. The power, you can say the power spectral density can be calculated with the help of nq dot omega, which is equal to j omega nq omega. Now, as PSD is proportional to the magnitude of the spectrum, so the power spectral density for the above expression is snq dot omega is proportional to omega square into mod of nq omega whole square. Now, the PSD for n naught t will be expressed as s naught omega is equal to, now note that q of omega c in the above expression is a constant, and again we can ignore this term as this is a DC term, and because of high pass filtration we can completely ignore this term. Now s naught omega will be equal to k square upon ac square into the value of snq dot omega, which I have already calculated, and put this value of snq dot omega into this expression, which is omega square into snq omega. Now, point to be noted, I have already squared k square upon ac square because I'm talking about the magnitude the whole magnitude of the expression, that is k upon ac is also considered as the magnitude part of nq dot t. That's why I have squared this term k square upon ac square. Now we know that the power spectral density of the quadrature phase component, which is snq omega, is equal to eta. for the bandwidth mod of omega is less than or equal to b, which I have already proved in the previous videos. So we can directly use the result. This is the power spectral density SQ SNQ omega, which is of magnitude eta from minus b to plus b. Now, applying the value of SNQ omega in the above expression, the new expression of Sn naught omega will be equal to Sn naught omega is equal to omega square k square upon AC square into eta for the range mod of omega less than or equal to b. Now we can plot this Sn naught omega. This is the power spectral density. It looked like a parabola which follows the equation of x square is equal to y upon 4a. Okay, so the graph will look like this from minus b to plus b. The scale is omega and this is Sn naught omega. Now as we have S naught and omega, which is the power spectral density, now we can calculate the output noise power, which is N naught is equal to 1 upon 2 pi integral from minus b to plus b Sn naught omega d omega is equal to 1 upon 2 pi integral from minus b to plus b. And now we can put the value of Sn naught omega from the above expression into this expression, which is k square eta into omega square upon AC square d omega. The above expression can be re-equated as, and we can solve the above expression as now it is equal to k square eta into 2 pi fm whole cube divided by 6 pi into AC square by 2. In this expression, AC square by 2 can be considered as the carrier power This expression can also be mentioned as maximum frequency of FM. Actually, this is the message frequency, the maximum frequency of the message. So this is the maximum frequency bandwidth of the input message MT whole cube divided by the carrier power. Point to be noted, this FM is the maximum frequency of message. Now from the above expression, it is clear that increase in carrier power increment in carrier, the output noise power and not the output noise power and not decreases. From the above expression, it is very clear that a carrier power increases, noise power decreases. So this effect is known as noise quitting effect. Note that the spectrum shape of Sn naught omega is parabolic in nature. I am talking about the shape. It suggests that you can see in this figure, this is the parabolic shape. It suggests that it suggests that maximum frequency content of MT face maximum noise that means as the frequency noise, or you can say frequency increases. Now as the frequency increases, the noise power also increases. Noise affects more on higher frequencies. In comparison to lower frequencies. That means higher frequency of the message face maximum noise content in comparison to lower frequencies. So to compensate this effect, To compensate this effect, we use preemphasis circuit at transmitting end before modulation. We can draw a block diagram to show the position of preemphasis used in the transmitter circuit. This is our MT and this is the preemphasis circuit. And the output of the preemphasis is passing towards the frequency modulator. This is the carrier for the frequency modulation and the generated value of phi FMT. This preemphasis is nothing but a differentiator which is nothing but a high pass filtration which is as shown in the figure. This is the input and the output. The transfer function, or we can say the magnitude transfer function for this preemphasis filtration or circuit is given as this is our mod of HP omega, which is the magnitude of the transfer function, or we can say frequency response. For preemphasis high pass filtration. This is clearly visible in this figure that when we feed our message into this preemphasis circuit, it clearly suppresses the low frequencies and boosts the amplitude of the higher frequencies. Now this is preemphasis, which preemphasis, which enhance the amplitude of higher frequencies in comparison of lower one. To minimize the noise effect on higher frequencies. Now, to normalize the effect of Preemphasis circuit. Deemphasis is used at the receiving end. This is our circuit of Deemphasis. As the differentiator effect can be compensated with the help of integrator. So this is very simple. Deemphasis is a simple integrator which is a low pass filter. Deemphasis circuit. The transfer function or the frequency response for the Deemphasis circuit is given by, it clearly reveals that it just remove all the changes done by the Preemphasis. That means it boosts the amplitude of the low frequency contained and in comparison to the higher frequency. So the effect of Preemphasis circuit can be normalized. For a same FM modulation and demodulation system, the transfer function of the Preemphasis and Deemphasis circuit is such that HP omega into HD omega is equal to constant. That means that means HP omega and HD omega are the invertible systems to each other, so that the effect of both will be neutralized. Above explained noise analysis is especially for small noise case, which was case 1, where AC is dominating over noise. Now, for case 2, or we can say the second case, where AC is much less than NCT and NQT individually, this condition is considered as threshold condition. Threshold condition. Now, in this case, the noise is dominating, and hence, for this case, the system performance completely degraded.